Okay, and hello and welcome to the next edition of Turbo Delphi Demos. I'm Nick Hodges, the Delphi Product Manager, and today I'm going to be talking to you about data types. We've done a little code in the past Turbo demos, but in this one we're going to talk a little bit more specifically about data types and exactly what those are and how Pascal deals with them. Now again, I'm going to open up a simple console application, and I'm going to use that to demo what the different types of data types are. Now, in the past few demos, we've been using we've been sort of declaring this simple thing called I equals integer, and we're saying, well, an integer is just a number, a whole number. Well, what exactly is an integer? Well, in Pascal, Delphi, an integer is a 32-bit number, whether it's a number in the range from 32 bits, and thus that will be and it's a signed number, so the numbers will go from -21474836448 all the way up to the positive number of that, 21474836648. So that means that the biggest number that you can assign to an integer is this number here. I can get that value, and then the smallest number you can assign to an integer will get that value as well. Okay, there are some other types of integers, however, some integers that cover slightly smaller ranges. For instance, there is the type short int. And that covers the range from just -127 to -128 to 127, i.e. 255, or a byte's worth of data. Similarly, there is the data type byte, which simply covers from 0 to 255. And then there's also the word type, which is a 16-bit integer, which covers that from 65535. Well, actually, I'm sorry. We'll put the comment there, the semicolon there, and we'll just declare that a type W. And those are some of your basic integer types. Let me go up and put the range up here for you as well. It's from here all the way out to there. And finally, the final type of integer that we can deal with, there's different types of integers, is the integer of the cardinal type, which is an unsigned 32-bit number which goes from 0 all the way up to this maximum value here. Change this here real quick. So those are the various different types and ranges of integers that you can use. Now, normally you would probably just deal with the native type for the CPU, which is the integer type, and it's the most efficient because that's the type of integer that the CPU uses natively. And since we're doing 32-bit development here, you use the integer type most of the time. Now, when I say that the value here is the highest value that you can have for an integer, what I mean is that if you try and add 1 to this, you're going to get a warning from the compiler telling you that it's overrun its bounds. You get an error. Oops, I'm sorry, I forgot a semicolon here. If I try and compile this again now, you'll notice I get a warning, and that warning that I get is constant expression violates subrange bounds. And what that means is that since I've tried to add 1 here to this integer value, to the maximum integer value, the compiler recognizes that and warns me that I'm going to get an overflow. It doesn't give me an error because actually, legitimately, the strange way that mathematics works inside of computers, you can actually add 1 to the maximum integer, and it actually will do what's called an overflow, and it'll overflow to all the way out to the next number at the far end. if you do this, but the compiler will warn you and tell you that you can't have a value bigger than this value here. And this is represented in Delphi code by the constant name maxint. Maxint. So these two statements that I'm typing here would be equivalent. Now those are the simplest number types that you can have in Delphi. And these are ordinal types, meaning they have an order to them. They're discrete and they have an order. In other words, 1 is smaller than 2, is smaller than 3, is smaller than 4. They're ordered, and thus they're very simple types and normal types that the compiler deals with. Now, not only does there standard types inside of the language, but Delphi also allows you to declare your own types. And one of the common types that you'll see declared in Delphi are enumerated types. And enumerated types are ordinal types. They have an order that you declare using your own identifiers. And to declare your own type, you use the keyword type, and then you declare your own type name. In this case, we'll call it tsuit. And now in Delphi, it's very common by convention to declare a type and call it type, and declare the type name with T, so tsuit. And then you can enter in your own identifiers for your own type. So for instance, we might type in diamond, heart, club, and spade, and that would indicate our type of T-suit for playing cards. We could even name this a little better, playing card suit, and we would name them diamond, heart, club, and spade. And now we would have our own enumerated type. And thus, once we've declared a type, we can declare a variable such as suit of type T playing card suit, and then we can make a declaration or assignment to type suit as simple as suit gets heart. And now suit would be holding the value of type heart, and that is an enumerated type. Now you can have any number of enumerated types, declarations in an enumerated type. You can use any identifiers you want as long as they're standard Pascal identifiers. And the standard Pascal identifier can have alphanumeric characters plus, I believe, underscores and numbers. Alphanumerics and underscores. Now I said that the enumerated types are ordinal types, so that means that I can declare an integer and assign to it the ordinal type of heart, for instance. And then if I typed write len I here, and I'll give us our trusty readlin so that we can see the output and maintain the output. Now if I run this, I'm going to check the ordinal value of heart, and in this case it should run and give us 1. Ordinal types are 0 based by default, so diamond is the order. The ord of diamond is 0, the ord of heart is 1, the ord of club is 2, the ord of spade is 3, and so on for any particular ordinal type. Now there's one particular ordinal type that is very specific to Pascal, and you'll use quite a bit, of course, and that is the Boolean function, or the Boolean type. Now Boolean is declared as a single type. It's Boolean equals, or Boolean is equal to false, true. That is, the ord of false is 0 and the ord of true is 1. And so Boolean types can only hold one of two values, and that is either true or false. So I can declare a statement here saying is true gets either true, or then I can follow that up with, of course, is true gets false. And of course I can also assign to any Boolean variable a value, a Boolean expression that will evaluate to either true or false, and in this case I is greater than 6, and this will actually end up evaluating to false in this code because the ord of heart is 1, and 1 is less than 6. So Boolean values are actually an enumerated, declared enumerated type in Delphi. Other languages use 0 as false and anything else is true, or 1 is true and anything else is false. It depends on the language, of course, but in Delphi, a Boolean is actually a enumerated type. Now, the other fun part of declaring types is that you can declare subranges. For instance, you can declare a type t under 100 as, say, 0, and I use 2 dots here, to 99. And that means that if I come down here now and declare another variable as just a variable under, call it t under 1 of type t under 100, that means that I can only assign a value of under to a value between 0 and 99. If I try and give it 100, the compiler will complain because I left out a semicolon up here. It'll complain because it'll say constant expression violates subrange bounds. I can't declare a value for under of greater than 100, and in fact I couldn't declare it to be negative 100 either. It'll give the same error. Now, you can declare a range of any ordinal type. So for instance, I can come up here and I can declare t red suit as equal to diamond to heart, like so. And now if I try and now I can declare a variable of type, we'll call it red suit, of type t, red suit, and now I can only assign red suit can only take either diamond or heart. That should compile just fine. Now if I try and compile, if I change this and change it so that try and assign the value of club to it, you'll notice the compiler will say, no, constant expression violates subrange bounds. You cannot do that. Some common ways to do this, some common things you'll see. For instance, you might declare a type lowercase, and it can equal from A to Z. And then of course you could do uppercase equals A to Z, and that's because cars are ordinal, and thus you can declare those types, and you can limit the types to those particular ranges. Okay, now the final type we're going to look at today, in addition, is another form of numbers, and those are real numbers, real types. And a real type is a value that is not as a number value that is not an integer. In other words, floating point values, i.e. numbers between 1 and 2. And of course there's an infinite amount of those numbers in between 1 and 2. There's an infinite number of real numbers. Now Delphi allows you to approximate to a very, very, very high degree all real numbers. Now of course the thing to remember about real numbers is there's an infinite number of them, but there's not an infinite number of states that your computer can be in. So therefore not all real numbers can be precisely managed by your computer, because there's an infinite number of them and only a finite number of states your computer can be in. So that means that floating point mathematics on a computer is an imprecise science at best, although there are certain data types that can mitigate to a large degree the errors that occur when you deal with real numbers, infinite number of real numbers on a finite computer. Okay, anyway, so inside of Delphi there are 6 real types. The first one is type real. The next one is type single. Then there's type double. Then there's type extended. There's type comp. And then there is type currency. Now, the particular values that these can hold are a little bit complicated. A real has actually been deprecated, and it's only maintained for backwards compatibility. It has 11 to 12 significant digits, and it is 6 bytes in size. The single has 7 to 8 significant digits, and it is 4 bytes in size. The double is considered to be the native floating point for your floating point unit, and it has 15 to 16 significant digits, and it is 8 bytes in size. Extended has 19 to 20 significant digits, and it is 10 bytes in size. Now, the comp is an unusual number, a little bit unusual type, in that it is a floating point value, but it maintains itself as an integer. It holds 19 to 20 significant digits. I'll explain that here in a sec. It's an 8-byte value, and it actually holds within itself, I'm going to have to use a little extra space here, it can hold values from -2 to the 63 plus 1 all the way up to the value of 2 to the 63rd power minus 1. So it's actually, it can be represented as an integer type. I think that error insight is coming from the fact that I've already declared a C from up here. So there we go, CO we'll call that. And the currency value is an interesting the comp actually is a 64-bit integer, as you saw, that holds integral values from the inside of this range. It's stored as internally and dealt with internally as a floating point value, but it actually can be assigned to and be an integer, 64-bit integer type. The currency value, again, has 19 to 20 significant digits. It takes up 8 bytes of memory, and it is guaranteed to be suitable for monetary calculations, i.e., it's stored as a scaled 64-bit integer with the 4 least significant digits implicitly representing the 4 decimal places, and those are guaranteed to be accurate with respect to the first 4 digits, so that you can use it for currency values. I mentioned earlier that real number calculations in any computer in the world, by definition, will be slightly inaccurate because you can't represent an infinite number of numbers on a finite machine. So currency is designed specifically to allow you to maintain real number values to the least 4 significant digits to the right of the decimal point, in order to guarantee that you get an accurate count and avoid rounding error. Okay, so those are the types of numbers, real numbers, floating point numbers that you can use. And again, you can make simple assignments to them. You could simply say D gets 3.14159, or E gets negative 3.222, whatever, such as numbers like that. And you can add them together as well. You can go E gets E plus D, and you can do all the multiplication and comparative functions or operators on real numbers, just like you can with floating point numbers. With floating, like you can with integers, excuse me. In addition, just as a note, you can also assign integer values to floating point numbers. So, for instance, e gets I is a perfectly acceptable value there, a perfectly acceptable statement. If you want to convert the other way, you can go. You can use you can use the trunc function on your floating point value, which will simply lop off the entire mantissa, or everything to the right of the decimal point, and return the truncated value. Or you can use the round function. Now, the round function will round to the nearest integer. So, for instance, if e gets a value of 2.6, then after this call here, I will be 3. And if e is 2.4, I will be 2. Now, the interesting thing occurs if e is 2.5. The round function will use Banker's rounding, which means it will round to the even number. So if e is 2.5, and here I will be 2. But if e is 3.5, after this function call here, I will be 4. And the reason for that is that half the time it'll round up and half the time it'll round down. So statistically, that all evens out. That's called Banker's rounding. A common problem for people to expect the round function to do what they were taught in elementary school or whatever, and I can't remember that far back. I think they either taught you to always round up or always round down, one or the other. But that leads to statistical anomalies biased towards a particular way that you round, either down or up. So Banker's rounding always rounds one way, rounds towards the even number, meaning you get a balanced rounding. Half the time it rounds up, half the time it would round down, statistically speaking. Now, as I was going through this, I realized I shortchanged you on the integer types. There's two other integer types, in fact, that I want to show you. One is the I64 int64 type, int64, 64, and that is a true 64-bit integer that ranges the same as the comp type. So let me copy this value here, and the int64 is an integer value that ranges across that same range. And then there's also, in addition to the word, there's the long word type. And that is an unsigned integer. An unsigned 32-bit integer, excuse me. And so it ranges from 0 up to, what is this, 4,294,967,295, which is the max value for long word. So if you need to have unsigned values, you can have unsigned values up to 2 to the 32, from 0 to 2 to the 32, instead of the negative range here, which is negative to positive range here, which is an integer. Okay, that wraps it up for your basic Delphi types. We looked at integers, filled you in at the end there. We looked at enumerated types, as well as subtypes, subrange types. Here's another subrange type here as well for just a regular integer, so I can move that up using drag and drop. There's some other subranges as well. And we also looked at the different types of floating point or real number values that you can have inside Pascal, Delphi Pascal. So that wraps it up for another edition of Turbo Delphi Demos. Thanks for your attention, and we'll see you again the next time.